Good afternoon, everybody. This is the first session for the 2022-2023 USACO season. You guys asked to complete those discussions, the December Platinum discussions during the winter break season. So we're going to do that instead of our normal process, which is one question per week. So we'll try to finish all those 3 questions in about 10 days time frame. So first, go Niners. So here are the 3 questions from last week's 2022 December Platinum. The breakdown, making friends, and the palindromes. Frankly, this year's problem is slightly easier than last year. So let's go, today we will go through the first question, which is a breakdown. Here is the problem. You have nodes. Each node has a weighted direct edge from each node to another -1 node in a graph. Right? So basically you have n square edges and have weight of between I and j. Then you want to find out the path, the shortest path from node 1 to node n with exactly k edges. Then that obviously we know how to do, right? It's standard, slightly modified SSSP. Right? The question we have here is, every time we're going to take away one edge. For example, in this case, we have three vectors, 3 nodes, right? So this is the weight matrix. And first time we're going to take away node from 3 to 1, then 2 to 3, and all the way. The question is, every time you take away a node, an edge, what is the shortest distance between node 1 to node n with exactly k edges? Okay, that's the question. So let's look at the problem, right? Let's look at the constraints. So first we have n, which is less equals 300, and then we have k actually less equal to 8. And we have 3 seconds to solve the problem. This obviously tells you can do O(n) cube, right? So how do we do this? We have from node 1 to node n, right? It goes through a set of edges. Let's say this is a midpoint, okay? Midpoint n. We have k edge, right? So each side is either, it's k. If k is even, since this is midpoint, then it's k divided by 2, right? If k is odd, is basically one side is k plus 1 divided by 2, another side is k minus 1 divided by 2. Right? So in another word, it's either round up or round down of k divided by 2. Right? If we can find the shortest path from this midpoint, okay? If we can find the shortest path from 1 to this midpoint, and the shortest path from this midpoint to n. Okay, if we can find that, then every time when I want to find from 1 to n, I just need to iterate through all those n minus 2 points. N minus, let's assume each of those n minus 2 points could be the potential midpoint. Right? So that, then I can solve that. So the question becomes, by the way, k is 8, right? So k minus 2 is less equal to 4. Right? So the problem becomes, how do I find the shortest distance from 1 to n with k less equal to 4, or shortest distance from m to k minus 2 with k less equal to 4. And those are the same problem, right? So let's just try to solve one of them. Let's say from 1 to m. If I can solve from 1 to m the same way I can solve from m to 2. Here's a trick, right? It's, if I want to simplify the problem, I can start from the whole graph, then every time I remove one. But much easier if I start from the reverse, right? So initially I have no path, no edge. Then add this edge. Then I can very easily figure out what is the shortest distance, right? Then I can add another edge. So then I add another edge. So now you can see you can do this by dp, right? Every time you add more edge. Okay, so you reverse it. So let's say dp of I, j, k is the shortest distance from I to j with k edges. Okay, so that's my annotation. You will find out is actually we can make it much easier. Remember, k, in this case, k less equal to 4, right? So every time, initially all those are infinity, right? I start from here, without any edge. So the question becomes, every time I add an edge, let's say I add from u to v. Every time I add from u to v, how do I update this? Okay, so if, let's say if u is 1, okay, in the first case, if u equal 1, right? So when I calculate from 1 to m, obviously I just need to refresh everything, right? So I just use my standard SSSP with k less than equal to 4. I can find out dp of 1 to any point of k, right? So that is a complexity of O n squared, right? If u is 1. Let's say if u not equal 1, okay, how do I do that? So if u not equal to 1, let's look at the different cases. If k equal 1, means I have to find one path, okay? So from, basically I need to find from 1 to any point, right, of j with one edge. But I'm not up, but this one is not updated because u is not 1, right? So there's no change, okay? So if k equal 1, so dp of from 1 to j of 1, no change, right? No change. My goal is, remember, my goal right now is to find out dp of from 1 to all the midpoint, right? with k less equal to 4. Right? That's my goal at this moment. Right? From 1 to midpoint. Okay. So k equal 1, no change. Okay. K equal 2. Let's see k equal 2. I need to go from 1. Let's say I have, add this edge from U to V, right? So k equal 2 obviously is the only thing I'm going to update is it goes like this, 1 to U, U to V, right? So then that's easy. dp of 1 to V of k equal 2 is the minimum of original dp 1 to V of 2 of dp of 1 to U of edge, one edge plus the weight of U to V, right? So, I mean, this one itself is the weight of 1 to U, right? So that's k equal 2. So that's easy. So let's see, what if k equals 3? Okay. For k equals 3, okay, I started from 1, right? So I have 3 edges. Okay, 1, 2, 3. The first case is U to V is here, right? The second case is 1, 2, 3. U to V is here. Okay, that's still easy. In this case, is the minimum of the original dp, right? Or this edge plus this edge plus this edge, right? So you basically have to iterate through all the points. You iterate through all the points V can go to, right? For each point that V can go to, you do the minimum of weight of 1 to U plus weight of U to V and plus weight of V to M, right? That's your shortest path from 1 to M. Okay, if it's this case, right? So you go through both of those, right? If that's case, it's still easy, right? The original dp value, or is dp of 1 to U with distance of 2, right? Distance of 2, that's the original minimum, plus the weight of U to V, right? This one will be calculated before, right? Okay, so k equal 4. Remember, with the maximum, I only need to do 4, right? That's why I'm trying to pick the midpoint. So that's the standard divide and conquer. Otherwise, if you go to k equal 5, k equal 6, that's just too many cases to think about. K equal to 4, couple of more cases, right? 4 edges. Same thing. If U to V is here, or U to V is here, or U to V is here. If U to V is here, then this is original weight plus this weight plus from here to here is dp of V to M with weight of 2, right? So then you have to iterate through all m minus 1 point, right? You have to iterate through all the m minus 1 point. Okay, so in this case, from here to here is dp of 1 to U of weight of 2. Then this is the weight, and this is another weight, right? That's endpoint. That's the one that is connected to you. Then from here is dp of 1 to u of weight of 3, right? From here to the weight of 3 plus this w, right? The minimum of those. Okay. So that's all 4 cases. Now, we need to find, if you look at all the cases we have here, okay? So I only used, if you look at all the combinations, I only used from 1, starting from 1 to u with all the possible case, or used I to j with k of 2, right? I did not, and k of 1 is just original weight. I did not use I to j, I mean, if I is not 1, of weight of 3 or 4, right? So I can actually, instead of calculating all those dp of ijk, I actually only need to calculate 2 cases. One is dp of from 1 to, let's say, to j with k, k less equal to, 4. You can say this is, you can call this, for example, you call this dp1. Okay. The other dp is I to j, any other point, but I only use k of 2. I don't need to use 3 and 4. Let's call it dp of 2, right? So basically calculate those 2 will make your job easier. So in above is basically how do I calculate dp1, right? So I can speed up, I don't have, how do I do dp2? dp2 is easy. Every time you add a node from u to v, because the k is 2, right? There's only 2 cases you need to update. One is like this, another is u to v, which is like this, right? So you only need to update, every time you add an edge u to v, you only need to update from I to v, where I will go to u, or you update dp of u to j, where v go to j, right? You only need to update those 2 cases, meaning the minimum of the original was this condition. Okay. Once you have those, look at it. Once you have this, then you calculated the shortest path from 1 to the midpoint, right? From 1 to midpoint, k less equal to 4. So you don't have to do all 8. Then for the same way, you can calculate it from m to n, right? So basically dp of, for the same way, you can calculate dp from, let's say, I to n with k less equal to 4, right? You can calculate the same. Then every time you want to do one of those queries, right? So you do, every time you want to do one of those, you just need to iterate through m of them, right? So each time you take n to query through of those, right? And you have n square edges, right? So you the n square times to, in this case, you have 9 times, n square times. So that is your ON3 algorithm. this is the solution. So what did we use? We used SSSP, right? A slightly modified SSSP just to find the shortest distance. We used DP, right? Then we basically used the greedy. If you look at K equals 3, K equals 4 case, right? Oops. And then it started with divide and conquer, right? We split into 2, okay? So that we can easily deal with all those cases. So that's the combination of the algorithm we use. Pretty straightforward, actually. Right? So the tricky thing is, number one, you figure out that you're going to use divide and conquer, right, to make the case simple, up to 4, then up to 4 edges. The second is when you calculate all those, don't go from the full matrix to every time you reduce an edge. Start from where you have no edges, and every time add 1, so you can DP it. That's a pretty standard trick to calculate and update the edges. So that's a solution for today. Thank you for your interest, and I know it's just past this Christmas. And take a couple of days to code it up. I think the official solution may be similar to this. Take a couple of days to code it up, and then over the weekend, we'll talk about the second problem, find friends. Or you can study the standard solutions, which I believe are same or very similar to what I described here. Okay, so enjoy your holidays, and I guess we will see you over the weekend to talk about the problem number 2.